Suppose that the second derivative of a function exists on a particular interval I. First condition, if the second derivative value is greater than 0, then f is concave up on that interval. That is, if the value of the second derivative for all the values of x on that interval is positive, then the function is concave up. Similarly, if the value of the second derivative of the function is negative for all values of x on that interval I, then the value of the function is concave down. If C is a point in I at which the value of the second derivative of the function changes from concave up to concave down or vice versa, then that point x is equal to C is called an inflection point. So during your exams, there might be questions asking you to find the inflection point of some particular function. So that will involve applying this test in order to find out where the concavity of the function changes. That is, where the sign of the derivative of the function changes from increasing to decreasing or decreasing to increasing. Let us look at some examples based on this. F dash C is equal to 0 does not necessarily imply that f has an inflection point at C. That is, the second derivative of the function equal to 0 does not necessarily mean that there will be an inflection point. We can look at examples of that also. However, in most of the cases, it does happen that the second derivative of the function, if it is equal to 0, then that is an inflection point. There are exceptions to this rule. However, as we can see, we are just moving into more generalized rules. At x is equal to 0, even though f double dash 0 is equal to 0, the value of the function is equal to 0. However, the concavity does not change. Suppose we look at this example. Again, it's a cubic function. So to the left of the point x is equal to C, the function is concave down, and to the right of the point x is equal to C, the function is concave up. At the point x is equal to C, the value of the derivative of the function is equal to 0. However, the second derivative of the function is also equal to 0 in this point, and therefore it corresponds to an inflection point. Let us look at another example. Obviously, it is clear from this diagram that the function does not have any inflection point, because both on the left side as well as the right side of x is equal to C, the function is concave up. That much is pretty clear just by looking at the graph of this function. However, what we get is that f double dash C is also equal to 0 at the point x is equal to C. So again, this is an example of a function which does not follow the rule of concavity of the function. That is, f double dash C is equal to 0. However, the point C is not an inflection point, because the fundamental fact of inflection point is that it's a point where the concavity of the function should change from one to the other. This is another example. This is probably the cube root of some function. So at the point x is equal to C, the second derivative of the function does not exist, and the concavity of the function is changing from concave up to concave down. And therefore, even though the second derivative does not exist, it is an inflection point because the concavity of the function is changing. Let us look at another example. Even at this example, the second derivative of the function at the point x is equal to C does not exist. However, the concavity of the function is also not changing. Therefore, this is an example of a function where the second derivative does not exist. However, it is not an inflection point. So the main point to gather from these four graphical examples is that the concavity of a function depends only upon the shape that a function takes and not on critical points. Critical points may or may not give inflection points. We can look at more concrete examples with the following problems.